Hello, Matthews Gatos here. In this video, we're going to talk about how to solve exponential equations. Let's get started. To solve an exponential equation, you're going to write both sides of the equation with the same base, because if the bases are the same and they're equal, the exponents must also be the same. For example, b to the n equals b to the m. See how the bases on both sides are equal? Well, if the bases are equal, the exponents must also be equal. So I want to practice how do we write things with the common base first. For example, 4 to the x plus 3 and 8 to the 5x. How do I write those with the same base? So I want to have the lowest whole number base. So I look at the lowest number, which is 4. Now I know I can't multiply 4 by itself to get to 8, so I need to go lower than 4, and that would be 2. So I know 4 is the same as 2 squared, 8 is the same as 2 cubed. But since 4 was raised to the x plus 3, I will take 2 squared to the x plus 3. Since 8 was raised to the 5x, I will take 2 cubed and raise it to the 5x. So here I have 2 to the 2 times x, 2 times 3. 2 to the 3 times 5x. So now I have product law. I keep my base the same and add my exponents. 2x plus 15x is 17x, and then plus 6. Now the nice thing about this is you can always check it in the calculator. You would just put your question in y1, your answer in y2. The check always happens in the table to see if you're right. So you can see I put question in y1, answer in y2, and you can see y1 equals y2, so I know I did it correctly. Let's try another one. So in this next example, I have 1 over 64 to the 5x. So I want to write that as the smallest whole number base. So my tip for you here is that if you want to change a base from a fraction to a whole number, the exponent will go from positive to negative. For example, 1 over 64, I can rewrite that as 64, a whole number, but then my exponent would be negative. So I'll have 64 to the negative 1 raised to the 5x, which is 64 to the negative 1 times 5x is negative 5x. But I wanted the smallest whole number base. So I know I can go smaller than 64. So I can actually go all the way down to 2. So if I take 2 and multiply it by itself 6 times, I would get 64. So 2 to the 6 is raised to the negative 5x, and then I just keep my base and multiply my exponents, which is negative 30x. So that would be 2 to the negative 30x, the smallest whole number base. So let's look at, now we know how to write the same base. How do we use that to solve? So again, I'm going to write both sides with the common base. So I look at 4 and 32. I can't multiply 4 by itself to get to 32, so I'll go lower than that and I'll go to 2. But before I do that, let's make 1 over 32 a whole number base by raising it to the negative 1. So I have 4 to the 3x equals 32 to the negative 1 times x and negative 1 times 5. Now they both have whole number bases, so let's go smaller. Let's go to 2. So 2 squared is 4, and 2 exponent 5 is 32. So 4 is raised to the 3x, and 32 is raised to the negative x plus 5. So I'll keep my base and multiply my exponents. Keep my base and multiply my exponents. So now I have an equation where they have the same base on both sides. The only way that can be true is if the exponents were equal. So 6x must equal negative 5x plus 25. So I have a nice linear equation to solve. I just want to get x on one side and number on the other. So I get an answer of 25 over 11. Let's now take this and apply it to word problems. So we know the formula on our formula sheet, y equals a times b to the t over p, where y was our final amount, a is our initial amount, b is our multiplication base or factor, t is time, p is period. These have to be in the same units. We also talked about the different ways to write bases, doubling, tripling, half-life, increasing, and decreasing. So let's keep all those things in mind. I want to do two word problems with you. So first one here, I have a bacteria culture that starts with 1,000. That's my initial value. And it doubles, that would be my base, it doubles every 40 minutes. So if it's doubling every 40 minutes, that's my period. I want to know the number of minutes it would take to the nearest minute for the population to reach 600,000. So that's my end value. So putting this all into the equation, I have 600,000 equals to 1,000 multiplied by 2 to the t over p, which is 40. Now, what I would normally do is write this, I think I'm missing a 0 here, there we go. I would write this with the same base. I can't multiply 2 by itself to get up to 600,000, so I can't solve this algebraically. So when I can't solve something algebraically, I always go back to a graphical approach. So I'll put left side in y1, right side in y2, and let's find the intersection point. So if I go into my calculator here, I have 600,000 and 1,000 times 2 to the x divided by 40. So the key to this is really setting your window setting. So remember, x is the number of days, y is the population. So let's go into our window. So we have to totally guess what we think that the time would be. And it's okay if we get it wrong. Time can't be negative, so I'll say 0. Now it doubles every 40 minutes. Actually, I'm going to try 400 because that's like 10 doubling periods. I think I'll definitely reach it by then. So I just want to kind of try and get it on the first shot, but if I don't, that's okay. I'll go up by 25s. Y is your number of people, and you want to go all the way up to 600,000. So I'm just going to go a little bit above that, and I'll go up by 100,000s. Did I do that right? One more 0. Perfect. Okay, your window setting does not have to be the same as mine. I just want to get a window setting where I can see the intersection point. So there goes 600,000. Here comes my graph. Ooh, I just snuck it in there. And I can see my intersection point. So let's calculate. Second, trace, option number 5 for intersect. And then I just press enter 3 times. Enter for the first curve, enter for the second curve, and enter to get past guess. And there we have our intersection point. So I can write that in my notes, and then I have to decide how I'm going to round. Okay, so I saw graphically that my intersection point was 369.1525, and of course the 600,000. There we go. So I want to the nearest minute. So to the nearest minute, that would be 369 minutes. So that's how you would solve that one. Let's try another one. So in this one here, we have an investment of $1,000 earning interest 6% per annum. Remember, per A is annum. It's just a snobby banking word for years. Compounded semi-annually, that means twice a year. How much would it be worth after 5 years? Okay, so we're starting with $1,000. Our base is per period. So I'm starting with 100%, all of my money, but I'm getting paid 600% for the year, compounded semi-annually. That means I'm getting paid twice a year. So each time I get paid 3%. So my base is going to be 100 plus 3%, which is 103%. Of course, we don't deal with decimal or percents, we deal with decimals. So it would be 1.03. Now, time would be 5 years, and the period, how long does it take to go through a cycle? Well, there's 2 cycles in 1 year, semi-annually, so it takes half of a year to go through 1 cycle. Y is what we're trying to figure out. So y equals 1,000 multiplied by my base, 1.03, to the exponent of 5 divided by 0.5. So because this doesn't have an x value, it doesn't go in y equals, it goes in our main screen. So we can just calculate that. 5 divided by 0.5, of course, is 10. So looking at that on the calculator, this is money, so we round it to the nearest hundredth. So after 5 years, it will be worth $1,343.92. Okay, let's take this same information and try another one where we're looking at how long it's going to take to double. So we still have our initial amount of 1,000, our base is still 0.03, our period is still 0.5, but I want to know how long it's going to take to double. So it was $1,000, doubling would be $2,000, and I'm solving for my time. So I write it in my equation. So I have y equals a, which is 1,000, multiplied by my base, 1.03, to the exponent of t over p. Now, because this one has a variable, I'm going to put it into my equation. So in y1, I'll put the left side, 2,000. In y2, I'm going to put my equation. So you can see in y1, I put 2,000. In y2, I put in my equation. So again, the big thing here comes with the window. So I want it to double. So I want it to go up to $2,000. That's my y value. So a little bit past. And then I just kind of guess what I think my x value is going to be. So I guessed it would take about 25 years. I'm sure I'll see it within 25 years. So I went 0 to 25 up by 5. And because I'm going up to 2,000, I just went a little bit past that 2,500 up by 100ths. So I put that into my graph and I calculate my intersection point. So I said, how many full years does it take? So it's this intersection point right here is at an x value of 11.7. So I want to know, do I round it at 11, which would be below that, or 12, which would be above it? So I want to know the number of full years. So at 11 years, you can see I am below 2,000. At 12 years, you can see I'm above 2,000. So if I want to know the number of full years that it's going to take, it is going to take 12 full years. So when we can't solve something algebraically, at this point here, all we can rely on is solving it graphically. So I have one last question for you, and that is, why did the banker eat lunch by herself? Well, the answer, she was a loner. So I hope this video helped. If it did, please give it a thumbs up and hit subscribe so I can help more mathies just like you. Thanks for watching, and I'll see you for the next one.